Okay, this is lesson 4, fundamental theorem of similarity. So we have been talking about dilations, which is another transformation of the plane. And we said that we've seen that dilations require a center of dilation and a scale factor that either takes a point in the plane and pushes it away from the center, or if the scale factor is less than 1, between 0 and 1, then it would pull those points back towards the center. So they're either pushing away or pulling towards. And any point in the plane can be dilated from that center. So we've looked at some examples. We've looked at what the definition is and some of the things that happen. And in this lesson, we are going to kind of experimentally verify some of the properties related to the fundamental theorem of similarity. So in this module, once again, we're talking about similar, and we talked about similar means, yes, it means same size, same shape, but possibly a different size, whereas congruency, same shape, same size. And we said that wasn't a precise enough mathematical definition. It won't be the one that you will use from here on out. It works in some cases, but not all. And so, so we're just looking at it more in depth. So we're going to be doing some measurements in this lesson. So you're going to need a couple tools. We'll come back to this page in just a minute. You're going to need a piece of binder paper and a centimeter ruler and a protractor to measure some angles. Okay, because we're going to see what happens to segments and angles under dilations. Okay, so let's start with our experiment. So what we're going to do is on this piece of binder paper, somewhere out in the middle, we're going to put a center O. That's going to be our center of dilation. And we're going to use the lines on this paper because they have some properties that are going to help us. And so these lines are parallel, right? There's no intersections of these lines. And so they're going to help us keep track of our scale factor and that sort of thing. So come down, I'm going to come down 3, but you could come down 2 or 3 or 4, whatever you like. You can do it just like me, or you can pick a different one because this is going to determine our scale factor. And so label that point P. And then we will draw the ray between O and P right here. I'm going to extend it up a little bit, just lightly. So we have ray OP. And so we're going to dilate this point P. So I'm going to pick a place for the dilation on one of the lines of the binder paper for convenience. Okay, so there's some scale factor that's dilated this point. Now we want to determine what scale factor would that be. Well, it's not double, right? So I know R isn't 2 because R equals 2 would have put it out here. One thing you want to notice is that these little segments here are all evenly spaced. And so if this is 3 units, this is 2 units. So they're longer than if I had drawn the line straight down like that, but they're all the same. So I can find a ratio that way of the units. Okay, so part of the definition of dilation is that the length of the segment from the center out to the dilated point, that's what this is, length of OP prime, is equal to R times the length of the center out to the original point. So R times OP equals OP prime. So what I'm going to do here, if I do a little algebra here, divide both sides by OP, then what you can see is that the scale factor is equal to the dilated length, OP prime, divided by the length from the center out to the original point. Okay, so if if the distance to OP prime is twice as far as the distance OP, then our scale factor is going to be 2. Okay, but that's not the case here. But we can just put in our values here for OP and OP prime. So the distance from O to P prime, which is the numerator of this fraction, is 5. And the distance from O to P is 3. So my scale factor for this drawing is 5/3. So kind of makes sense because it would be 6/3 or 2 if I had gone out 3 lines again. Okay, so it's 5/3. It's a little bit less than that. Okay, so we have a scale factor and we have our center of dilation. So let's do another point. So we're going to label a point Q somewhere over here. I think I'm going to take it out a little further. So here's Q, point Q. And we'll draw the ray so that we're going to also dilate point Q. So I'm going to draw it right here. All right, so we've placed Q also 1, 2, 3 lines out. We want to dilate Q by the same scale factor. So we just have one dilation. So that means that Q is going to come, Q prime is going to be out here on, for me, on the 5th line. Should be on the same line as P prime. Okay, so scale factor is 5/3. Now notice we still have these even distances. So the ratio is 5 units to the dilated point and 3 units to the original point. So the scale factor is still 5/3, or 5/3. Okay, so we've got P and Q and P prime and Q prime. Okay, so we know if we measured these segments, and we're going to do it in just a minute. We're verifying this theorem or some of these properties of similarity, properties of dilations and similarity. We're doing it experimentally. We're doing it on paper. We're going to do some measurements and we're going to do some calculations. Oh, the other thing you need is a calculator. You're going to use a calculator for this because we're going to be doing a lot of division. So what I want to do is I want to connect the line PQ, or segment, and the segment P prime, Q prime. So we've got these two segments here, and they are parallel. And that's important to notice. In addition to that, I want you to think about some angles in our diagram. So really everything in this plane is being dilated. So if we think of this angle here, OPQ, so angle OPQ, I'm going to write over here, and compare that to angle OP prime, Q prime. Okay, go ahead and measure those angles. So mine is just over 50. It's about 54 degrees. And if I come up here and look at this one, it's the same. So these two angles are equal and they are 54 degrees. Okay. Now we might have been able to know that without even using a protractor. If you think about the fact that this line extends, PQ extends here, these are parallel lines. They're cut by a transversal. So think about what these angles right here are. Those are corresponding angles. And I could use a translation to show that. And we did that in the last module. So what about angles? What about angle OQP? Did I put it in there? Angle OQP and angle OQ prime P prime. I keep forgetting though. OQ prime P prime. What about those angles? What could you tell me about them? Okay, so for the same reason and without using a protractor, we could say these angles are equal to one another. So I'm going to mark this one over here with 2 tick marks just to show that these are corresponding angles. Here's a transversal cutting through my parallel lines. And again, this angle would translate right up to that one along this vector. So those are equal angles. Okay, so now what we want to do is we're going to be using the centimeter ruler. We're going to measure accurate to, these are centimeters, we want to be accurate to the 1/10 of a centimeter. Okay, and we're going to do some calculations and we'll have some error, and that's fine. We'll take that into account. So right now, you should pause the video and measure OP and OP prime. So those 2 segment lengths. Yours will be different than mine. So I'm going to measure mine, you're going to measure yours. Okay, I've measured segment OP, and mine is 2.6 centimeters. Yours is going to be different depending on the angle. So even if you went down 3 lines, if your angle is not as steep or steeper, then you're going to have a different result. So use whatever yours is, correct to the 1/10 of a centimeter, which is a millimeter. And my OP prime is 4.3. So it's not twice as big, it's less than twice as big. So what I want to check is, I want to know is this true? Is OP prime equal to my scale factor R, which is 5/3, times OP. So this is the calculation I'm going to do. OP prime is 4.3. So I want to know, I'll write it down here. Is 4.3 equal to, put a question mark, 5/3 times 2.6. All right, so I can just put that in my calculator. I'm going to do 2, so I'm doing 2.6 times 5/3, so that would be right over here. So 2.6 times 5, I can hit equal, but it will work either way, times 5 divided by 3, and that's equal to 4.33333. So this is 4.3, and this is approximately equal to 4.33333, like that. So it does check out that OP and OP prime are, the scale factor 5/3 does work. Okay, so do the same thing with OQ. I'll do my work, you do yours, and we'll come back and check again. Okay, so for my next set of measurements, I have OQ right here is 3.8 centimeters. OQ prime is 6.4 centimeters. And so I'm going to do 5/3 times 3.8. And maybe I went too fast on that before, but to do 5/3, I'm going to multiply. So 5 times 3.8, and then that result divided by 3. So 5 times 3.8 is 19. Divided by 3 is 6.3333. So I've got 6.3 repeating is approximately 6.4. If you're off by 1/10 of a centimeter like that, that's reasonable because we're having to round, sometimes it's in between. So there's human error here. So this is close enough to show that that ratio is holding for both of these. Okay, but we would expect it to. We would expect those ratios to hold because we counted it off. We counted 5/3 as our scale factor here. So what we want to do now is we want to look at a segment that we didn't dilate directly, but that is part of our dilation, and that's this segment, PQ. So PQ is a segment in the plane, and P prime, Q prime is the segment joining those dilated points. And we already said they're parallel, but now we want to check to see if they have the same similarity as these segments that we dilated directly. Okay, so is the scale factor that's enlarging this also 5/3? All right, and we did see in some triangles that we dilated in an earlier lesson that it is, but we're going to verify it experimentally here. And we're really going to verify this because all of you are doing slightly different measurements here. You might be using a different scale factor. You're using different angles coming out here. So we're going to find something out. So what we need to do is find the length of segment PQ. And we want to find the length of P prime, Q prime. So those two segments. Now remember, again, yours are going to be different from mine, but they should be, we're going to see that it's multiplied by your scale factor. We're going to check for that. Okay, so go ahead and pause the video and do that, and I'll make my measurements. Okay, so I measured my segment PQ, and it came out to 4.7 centimeters. And then P prime Q prime is 7.8 centimeters. So I want to know if my scale factor times PQ is going to give me that PQ prime. In other words, are they in proportion to? So I'm going to do my calculation here. So I've got 4.7 times 5 divided by 3 is 7.83 repeating centimeters. Okay, and I can compare that to my measured length of P prime Q prime, which is 7.8 centimeters. Okay, I'll just be honest here. My first one was off because instead of 4.7 here, I had 4.2. So I had just read my ruler wrong. So if yours don't come out close enough, you might want to go back and remeasure. Okay, so this should actually be, this is somewhat surprising because we didn't actually dilate this segment. We dilated kind of these segments and measured those for the scale factor 5/3. But these segments end up having the same properties as the segments that we dilated directly. So that's kind of interesting. Okay, so what I'm going to have you do now is I'm going to have you mark a point, we're going to call it A, here inside of our, between P and Q. And then we're going to put a point B over here on the other side of Q. Okay, and we're going to dilate these points. So you can go ahead and do that. I'm going to pause and draw my rays and label A prime and B prime. So go ahead and do that and come back and make sure you did it correctly. Okay, so here your paper should look something like this. I've labeled my point A between P and Q, out 3 units from my center, and then B on the other side of Q out here, and also 1, 2, 3 units on that same line. And so by drawing the rays, I can see where A prime and B prime will end up. Okay, so the question is, and kind of our experiment, and you should do some of these measurements, is we have lots more segments now. So we could talk about segment PA and P prime A prime. We could talk about AB and A prime B prime. And what we want to know is, are those in proportion? Are they dilated by the scale factor as well? So we could look at any of these segments. PA, we've already looked at PQ. We could look at PB or AB. And then we could look at their dilated partner and check for that. So I'm going to go ahead and I'm going to look at segment AB and check it for dilation. So it looks like AB is just between 4.8 and 4.9. I'm going to go with 4.8. So segment AB, the length of AB is 4.8 centimeters, and it's dilated length is, okay, so its dilated length is 8.0. So A prime, B prime is 8.0 centimeters. So I'm going to do my calculation here to make sure that that is the scale factor times, so let's go, I already did it here. So let's see, we've got 4.8 times 5 divided by 3, 5/3, is equal to 8. That one came out exactly. So, so 4.8 times 5/3, the scale factor, is exactly equal to 8.0 centimeters. Okay, so we've checked, that's our work for AB. We've checked PQ and PQ prime. What do you think? Do you think these other segments are going to be also be dilated by the scale factor? We could try QB. We'll do one more. We'll do QB and Q prime B prime. So let's see. QB, there's more room for error in these little ones. Looks like 1.4. So length QV is, what did I say, 1.4 centimeters. And Q prime B prime, which is its dilated partner here, is 2.4. Okay, let's see if that works. Might have a little bit of margin of error there. 1.4 times my scale factor, 5/3, and we'll see what that is. Is 2.3. 2.3 repeating. So that's pretty close to my measured length over here. I measured it at 2.4 and I calculated it at 2.3. Okay, so my measurement isn't too far off. It's within a tenth of a centimeter. Okay, so we could check those other segments that we talked about, and all of those should check out to be proportionate by the scale factor. Okay, so what I'd like you to do now is to think about what we've done. We have a dilation with a scale factor and a center, and we've dilated several points here, 4 points. We have the segments coming from the center of dilation out. We have segments that go between pairs of dilated points. And we found that they're all in proportion to one another by the scale factor. And we also found that corresponding angle measures are all the same as well when they're dilated. So, I mean, we could look at even this angle here, OQB, OQ prime B prime, and the angle measures are the same. So what you're trying to do is paraphrase that, and then we'll come back. And what you're paraphrasing here is really the fundamental theorem of similarity that we're talking about. So work on that and then come back and I'll write it out for you. Okay, so we kind of verified experimentally this rule, and it goes something like this. So given a dilation, or something to that effect, if we have a dilation. So I'll say given a dilation with center O and scale factor R, we'll call it, write it out. Scale factor R. So we have a dilation with center O and scale factor R. If we pick points, we're going to have points O, P, and Q. And so O is, of course, our center. P and Q are any other points that are not collinear. We don't want them all in the same line, because then that doesn't illustrate what we're talking about. Does collinear have two L's? I can't remember. I know. I know what to do when I don't know that. Not on the same line. Okay. So we're given a dilation with center O, scale factor R. We have points O, P, and Q not on the same line. And what we're saying is that, I'm going to put and here, and points O, P, and Q not on the same line. We're saying that the segments formed when connecting P and Q and P prime and Q prime are parallel. Okay, so they're always going to be parallel. We worked ours out. Ours are parallel, and we used the lines on this line paper to create parallel lines. But we also use the scale factor to show that they would be parallel. We'll see some other examples of that in a minute. So those segments are parallel, and what's even more interesting is that the length of P prime Q prime is equal to the scale factor times the length of PQ. So we're saying they're in proportion. They're in proportion to our scale, with our scale factor in proportion. Okay? And so P and Q could be any points, and we chose more than just 2 points. We chose extra ones, and we showed all those segments, AQ, PB, all of them. I didn't measure them all, but any ones that we'd measure, we would find this relationship to hold. And so two things are happening with this dilation. So we're given this dilation, and when we connect these dilated point segments, PQ and P prime, Q prime, they are parallel and they're in proportion by the scale factor. And that's pretty cool. And we're going to show, we're going to see some pretty interesting things with using a dilation to create a similar figure. Okay, let's work on this exercise that is in your notes now. So in classwork for lesson 4, you have exercise 1, and it has sections or parts A through E. And we're going to use this diagram for it. So you have this diagram, point R and S, and I can make these letters bigger for you. So here's point R, here's point S, and here's point R prime, and there's S prime. And we're told that they've been dilated from center O, and that the scale factor is R equals 3. So this drawing is not to scale, but part A says if length OR is 2.3 centimeters, then what would be the length of OR prime? Okay, well, the length of OR prime. Now you can try these on your own. I think you can try them all on your own. And I'll just go through them here to check. But based on what we just did with the binder paper, you should be able to follow these directions and do it. Okay, but I will go ahead. So OR prime should be 3 times the length of segment OR. And so since segment OR is 2.3, OR prime is 3 times 2.3, which is equal to 6.9, and it's centimeters. Okay, now it's not going to measure out to that because this diagram's not to scale, but you get the point. Okay, so if length OS is 3.5, what is OS prime? Well, length OS prime is going to be our scale factor times the length of OS, which is 3.5 centimeters. And so that is equal to 10.5 centimeters. Okay, so now we're told to connect point R to S. So we're finding a segment in that plane. And there is R and S. And we're also going to connect R prime and S prime. Okay. All right, so notice that those segments are parallel. Both points R and S have been dilated by the scale factor, so the segments containing those are going to be parallel. And the fundamental theorem of similarity tells us that. So they are parallel. I'll write that a little more formally. The lines R S and R prime S prime are parallel. Okay, and what else do we have? What is the relationship between the length of RS and the length of R prime S prime? Well, the fundamental theorem of similarity tells us that the length of R prime S prime is going to be the scale factor times the length of RS. Okay, and what do we know about angles? So let's look at the next. Okay, and we could also substitute 3 for the scale factor here. So R prime S prime should be 3 times RS. And we're asked to identify pairs of angles that are equal in measure. And how do we know they are equal? Well, we know that angle ORS, the measure of angle ORS is equal to the measure of angle OR prime S prime. And we know that the measure of angle OSR, that's this one right here, is equal to the measure of angle OS prime R prime. So this angle is equal to that angle, and this angle is equal to that angle. Whoops, you didn't see that. Those two angles are equal, and those two angles are equal in measure. And we're asked to say, how do we know they are equal? The angles are corresponding angles of parallel lines. So by what we explored in the last module, and let's see, so they are parallel lines, and there's a transversal here and a transversal here. So they're corresponding angles of parallel lines, and that's how we know that they're equal. Okay, so real quickly, just to kind of summarize what we did in this lesson, in your problem set, at the top of your problem set, is a summary that states the theorem that we're talking about here, which says that given a dilation with center O and scale factor R, then for any 2 points P and Q in the plane, so that OP and Q are not collinear, the lines PQ and P prime Q prime are parallel, where P prime is dilation of P and Q prime is dilation of Q. And furthermore, not only are they parallel, but P prime, Q prime, the length of that segment is the scale factor times the original segment. So just kind of bullet points here. So by saying we have a dilation, what we're saying is that the length of OP prime is equal to R times length OP, and And we have another point Q such that the length of OQ prime is the scale factor times OQ. Okay, and that's just saying we have this dilation from center 0. So that's this point. Given a dilation with center 0 and scale factor R, we know that that's true. So if this is true, then if I look at just the points P and Q, leave out the center of dilation, then segments PQ and P prime Q prime are parallel. PQ and P prime Q prime are parallel. And the length of P prime Q prime is equal to the scale factor times the length of PQ. Okay, so that's just another way of saying it. If we have this dilation, if this point P is dilated to P prime by a scale factor, Q is dilated to Q prime by a scale factor with center 0, then those segments containing those points, the original points here and the dilated points, are parallel. And I bet you didn't think I was going to find that, huh? And P prime Q prime is equal to the scale factor times the original segment length. Okay, this is going to mean a lot when we're dilating polygons, whole figures, because it means that all the lengths are going to be in proportion and all the angles, this doesn't talk about angles except that we know that we have parallel lines going here. The angles measures are going to be preserved. So we'll see that in later lessons. Okay, so in this problem set, you're going to go through the same type of exercise we did on the binder paper, this one that we did. You're going to go through the same process, but with a scale factor less than 1. Between R and 1, R is between 0 and 1. So instead of your dilated points being pushed away, you're going to have them coming closer. So make sure you choose a P that's kind of farther out so you can come in for your scale factor. So you're going to find the scale factor, and you get to choose the number of lines on your notebook paper, and then follow the directions. Okay, and if you're unsure of what to do, you can check the solution key. Okay, and then it's going to guide you through some questions to ask about that. And then there's a few problems that you're going to do on graph paper. So it gives you some different dilations where you're going to find the scale factor. So remember when you do this, that's another good thing to put on here, that it's real easy to find the scale factor, because remember the scale factor is just a ratio, and it's the ratio of the dilated length. So, well, let's just write it out. The dilated length over the original length. You might want to write that in your notes, because if you need to calculate a scale factor, you can just take any dilated length, compare it to the original length, and that will give you your scale factor. Okay, so this would be like the OP prime and the original length being OP. Okay, for example, this is an example. So this is just the general definition of scale factor in our with these dilations. Okay, have fun with that.